Okay, this is a demonstration that I typically do with my traditional classes. It's a vacuum tube, and at the back, what is a vacuum? A vacuum is when you remove air molecules. So essentially you take a pump and you pull out all the air molecules in this tube, leaving nothing inside there, no air. And then what you do is you turn the tube upside down and let a penny or a coin and a feather fall. And they actually do fall at the same rate. And the question is, well, why? First of all, when you turn the thing upside down, they do fall, they do speed up. So that tells us that we do have a situation of acceleration, right? The forces acting on each of the objects they're not balanced, they're accelerating. So the question is, okay, well, what are the forces acting on these objects? Well, weight, right? Isn't the Earth pulling on both these things? One mistake that students will make is to say that the force that the Earth exerts on each of these objects is the same. That is simply not true. The force that the Earth exerts on an object is what's called the object's weight. Does a penny weigh the same as a feather? No. The penny weighs more, right? So I can draw the force acting on the coin, and I'll label it as WC for weight of coin, and I can draw the weight of the feather, right? And notice that I don't draw them the same length because they're not the same weight. The feather weighs a whole lot less. So the next question is, well then, how the heck can I get the same acceleration for them, which is indeed true. They both accelerate, they both fall at the same rate. How the heck is that possible if the weights are different? Because haven't I figured out, are there any other forces acting on these things? No, there's no force, there's no air in here, so there's no air resistance. So therefore, the only force acting on each one is the weight. How the heck do I get the same acceleration? Remember, this is very, very crucial. Acceleration is not just about the net force acting on an object. So if I want to find out the acceleration of the coin, I would put the net force acting on the coin, which we've just said, the only thing that's acting is weight, and therefore when I add the weight plus nothing, I want it with weight, divided by the mass of the coin. Right? Now if you recall, when I defined what weight is the mass of an object times g, times gravitational acceleration. So I have the mass of the coin times, I'm just rewriting what weight is, divided by the mass of the coin. Now notice I've got a mass of the coin here in the numerator, a mass of the coin in the denominator, and therefore my coin has an acceleration of g, 9.8 meters per second per second. Can I do the same thing for the acceleration of the feather? You betcha. And this explains why they both accelerate with the same rate. What's the net force acting on the feather? It's the weight of the feather. Then I have to divide by the mass of the feather. That's Newton's second law. The acceleration of an object is directly proportional to the net force acting on the object and inversely proportional to the mass of the object. And of course, weight can be rewritten as mass, in this case the mass of the feather, times g. And I divide by mass of feather. And this, my friends, is how you wind up with the acceleration of each of these objects being the same, despite the fact that the net force acting on each of the objects is different, because acceleration depends not only on the net force, but also on the mass of the object.